Hello, everyone. Well, thanks for your kind words, and thanks very much for inviting me back again. It's always nice to be asked to come back. It's when you don't hear anything at all that you start to get worried. So I'm joining you from my shed in sort of sunny England, where over my shoulder you can see one of my prized possessions, which is a Star Trek uniform signed by Captain Kirk, which is quite exciting. It's still to go on my wall, so that should tell you something about my tendencies towards geekdom. But I'm really happy to be here to talk about the subject of scale, flow, and microservices. So this is a topic that I became fascinated with, well, not microservices, I'll come to that, but the idea of scale and scaling laws that emerge in different areas of nature and in different organizational contexts. I became fascinated with it a few years ago now. And I've done quite a lot of research into this, and so I thought I'd like to share some of the research that's been going on over the last few years, and also share some of the ways I think that we can learn from nature and from these natural phenomena with respect to software architecture, organizational design, and team design. So really, that's what this keynote's about. So I'll jump into it pretty quickly because there's a lot to get through, from mice to elephants to cities to Walmart to all sorts of different topics via the principles of product development flow, the 4 key metrics, accelerate, team topologies, and all sorts of things. So I'll kick off straight away with a quote from myself, because if you're going to appeal to authority, you might as well appeal to yourself. That's my head just growing bigger and bigger and bigger as I say that. But myself and Martin Fowler, we said a couple of years ago now, 2014, when we defined microservices, that there's no such thing really as a true definition of microservices. Instead, there were a set of characteristics that we described, that we saw organizations that were implementing microservice architectures, they tended to follow these characteristics. And these are the characteristics we identified. So, I'm sure these have become familiar to people over the years as microservices has developed into almost the sort of default architectural style these days. But one of the things that I'm kind of interested in with this research into complexity science is that a lot of these have some things in common. And there's a lot of the reuse of the word decentralized. There's a lot in here about pushing responsibility out to the sort of nodes in a team, pushing responsibility down, pushing governance down. In software architecture terms, pushing things like data governance down, isolating data governance on a per team basis, and these kinds of things. And also this idea of not having centralized smarts in your kind of in your enterprise service buses or your API gateways, but pushing the smarts out to the endpoints to the services themselves. And things like preferring choreography over orchestration and so on. So a lot of these things are about breaking things up into smaller bits and pushing responsibilities out into those smaller bits. And I sort of got to wonder, well, whenever you see something that's repeating like this, is there some sort of underlying set of principles, even below these sort of principles, that are going on? So is there almost like a sort of underlying physics of why service-oriented architectures, and in particular the sort of the microservice style of decentralized, smaller services, is there a set of underlying principles behind them? And this sort of came to a head when I was not this February, but the February before, just before the UK entered our first lockdown, pre-pandemic. I was at an event. Well, I'm very lucky in my job. I get to spend time with your good selves, but also with smaller groups in workshops and so on. And I got to spend some time at a workshop with a set of software architects at a place called Shoal Bay East in Anguilla. So this is Anguilla in the Caribbean. And there was a group that came together to discuss sort of things that are on the forefront of software architecture better practice at the moment. There's a bunch of people who sort of go, people like Gregor Hopper, who wrote Enterprise. Who wrote the Enterprise Integration Patterns book, and various others. In fact, in this one, would you believe that Melvin Conway was actually at the event? So Mel Conway is a real person. Mel Conway actually exists in real life. He's not just like a made-up name from a paper from the late 50s, late 60s. That's Mel on the right in this slide. And we started talking about organizational design in the context of Conway's law, in the context of how teams fit together. And one of the things, this is Adrian Cockcroft, who's formerly at Netflix. He was talking about how at Netflix they sit their teams next to each other, so the principle of locality, right? So if one team needs to talk to another team more than anyone else, they'll sit them next to them. So the API team, the UX sit next to the platform team, sit next to the services teams, and so on. They've designed the office that way, their office space. And Mel was completely blown away by this, obviously. I wrote this paper years and years ago, and suddenly I'm told that all these unicorns are sort of organizing their offices according to it. How bizarre. But anyway, another thing that came out in this workshop was someone was talking about Amazon and why, in particular AWS, and why AWS are producing so much software at the moment. So if you try and keep up with AWS and the amount of just new software products that they're producing, it's almost impossible to keep up with the number that they're releasing. Every sort of couple of months, there's a whole tranche of new products being released. And one of the things that was said, which was I just couldn't believe, I couldn't get my head around, was this idea that for AWS, the bigger they get, the easier it is to get bigger. So the more people they add, the easier it is to add more people. The more products they build, the easier it is to build more products. So instead of following the received wisdom of our industry, which is as you scale, things get slower. I mean, that's certainly been my experience. Summarized in the quote from Fred Brooks' Mythical Man Month decades ago, adding manpower to a late software project makes it later. In comparison to that, opposite to that, AWS seem to be growing faster and faster and faster. They're accelerating in their growth rather than slowing down. And that sort of chimed with some of the things I'd heard about their practices around team organization, about the use of platforms, the use of two pizza teams, and so on. So I sort of went off and did some digging behind the scenes. Now, I appreciate for the data scientists in the room, this is very few data points to be drawn a conclusion from, but this is essentially a log plot of Amazon Web Service revenue versus employee count. Well, revenue versus Amazon employee count. So essentially what this graph says is it's a straight line. It's a power law with an exponent of 1.15. So what that means on this log graph is that AWS or Amazon are growing super exponentially fast. As they double their size, they get more than double the amount of revenue. And actually Andy Jaffe showed a very similar slide to this, or graph to this, at AWS reInvent at the back end of last year, back end of 2020. So this is really interesting because that's kind of not really how companies should work according to received wisdom. As you grow, as you double in size, you shouldn't get more out than you put in. So why is that? And in order to explain that, we're going to have to go on a brief and almost certainly incomplete introduction to nonlinear dynamics and complex adaptive systems, or complexity science. So here's my first question. It's rhetorical. I can't really poll everyone in the room. But what do mice and elephants have in common? Well, there's an interesting fact about mammals. And one interesting fact is that, for example, all mammals share approximately the same number of heartbeats in their lifetime, right? Also, all mammals share the same blood pressure. So the blood pressure of a mouse is the same as the blood pressure of a dog, is the same as the blood pressure of a human, of an elephant, and of a blue whale. And the blue whale has the same number of heartbeats as a mouse does. So what do they have in common? They have those things in common, right? But they also have another weird thing in common. They have this scaling law in common related to what's called the metabolic rate. So how many calories they consume, essentially. So as an animal, as a mammal doubles in size, as you get double the amount of stuff, actually, you get, you've double the number of, it's actually not even double the number of cells. You have to the cube number of cells more when you double the size of an animal. Then the metabolic rate of that animal doesn't also double. You don't need to eat twice as much, consume twice as many calories as something half your size. In fact, you consume 3/4 of the amount of calories that you should. So metabolic rates in mammals, they follow the scaling law with an exponent of 3/4, 0.75. You only need 75% of the calories of something half your size, which is kind of counterintuitive. And what is the thing that gives? Well, the thing that gives with mammals is that cells age slower the bigger the animal. The metabolic rate slows, and cells actually age more slowly the bigger the animal. And this is why, for example, elephants and blue whales, there's a sort of paradox. Even though there's lots more cells in an elephant than there is in a human, elephants rarely suffer from cancer because their cells age so slowly. Another example of a power law in nature. What do mom and pop stores and Walmart say have in common? Well, remember what I said about Amazon's revenue. Typically, and there's less data on this than with mammals, it's less widely studied, but so the error bars are bigger on this graph. But typically, as a company doubles in size, you don't get double the revenue out. You get normally about 85% of the revenue out, which is very, very different to the figure of 115% that AWS or Amazon again. So revenue scales with number of employees following this other scaling law. As a company doubles in size, it generates about 85% of that revenue. And finally, as an example, cities. I first did this talk as a keynote in Germany, so I kept the examples in German cities. But what do Hamburg and Leipzig have in common? As you double the size of a city, or from a village to a town or whatever, what changes? Well, actually what changes is you have to spend less on infrastructure than you might think, about 85% of the amount of infrastructure. And this is true for road length, for number of petrol stations in cities, number of restaurants, for water pipes, electricity cables. As you double the size of a city, you don't double the size of these things. You actually only have to expend 85% of the amount of money, say, on these things, or of the length of piping for water supply and so on. So this is kind of interesting, three different power laws that exist in nature, and what these demonstrate is something called sublinear scaling, or what we talk about in finance terms as economies of scale. So as companies get bigger, they only have to spend 85% on infrastructure, economies of scale, as they double in size, but they only also get 85% of the revenue out. And as mammals get bigger, they only have to spend 75% of the calories that you would expect, and also for cities too. This is interesting because there's this great book which summarizes a lot of the original research, which is called Scale. I've got a reference to this at the end. And in that book, Jeffrey West writes, quantities that do not change when other parameters of the system change, they play a special role in science. And that was drummed into me when I read physics as an undergraduate. If you start to see similarities, regularities in places, straight lines on graphs or so on, maybe there's something interesting going on and you should go and have a look. So as I say, this is an example of a scaling law. So we've all become very familiar with this idea of scaling laws when we're talking about the pandemic, the R number, exponential growth. But what we're talking about here, if you plot on a log-log graph, exponential growth looks like a straight line like this. And what we're talking about is sub-exponential growth. So sublinear scaling. As one quantity doubles, the other quantity increases by less than double. Now, complexity science, I guess, came out of a sort of research into chaos theory. And there's an institute set up called the Santa Fe Institute in New Mexico by a bunch of current and then Los Alamos physicists in general, but also they then attracted behavioral economists and biologists and chemists and so on to study what complexity means. What do we mean when we say like something is complex? And the interesting thing about the research they've been doing in Santa Fe, that they found that these scaling laws, those power laws with the straight lines for mammals, cities, and organizations, they can be explained by mathematically, with a mathematical model, using three very simple principles. And these principles are the following. So the first is this idea of a space-filling fractal network. So in this case, we've got a hierarchy. You can think of this as the blood supply in your body. So, the heart at the center of this, and then this graph of blood vessels that come off your heart, supplying energy, essentially nutrients to the cells in the capillaries. In cities, it's houses and the people in the houses, and in offices, it's people doing work. You then got this idea. Well, I'm trying to persuade our staffing team to start calling us this in Thoughtworks, but invariant terminating units. So as I say, this is the end points of these of these graphs. So people, as I say, in organizations. The key thing is, or cells in mammals, the key thing is that they are self-similar with each other. From 10,000 foot, I am self-similar with my colleague on the call, Corny, to an extent within error. And then you've got the first thing is, the final thing, rather, the final principle is this idea of optimization. So the three different systems, biology and socioeconomic life of a city and companies, are optimized either by market forces or, in the case of mammals and biology, by evolutionary forces. So feedback happens on an evolutionary scale for mammals, but also much faster, obviously much faster for cities and organizations. But these three things can explain those power laws that I mentioned earlier. And the interesting thing about complex adaptive systems is that they're everywhere, right? We work in complex adaptive systems. Our team that we're in is a complex adaptive system. The society that we're in is a complex adaptive system. Our bodies are complex adaptive systems, and the people we talk to are cases. And they can be described by these three simple principles. But the key thing is that mathematics points to the fact that with hierarchical networks, like blood supplies, like road networks, or sewage systems, or water supplies, or information flow, or network cables, hierarchies imply sublinear scaling. So you get economies of scale. As you double one thing, you get less than double the other thing out. So if you double something in size, you don't double the other quantity. And as I say, they're everywhere. The teams we work in, the software systems that we're building, and the organizations in which we are working. This brings me to this idea of, AWS getting faster. Why is it that how is it possible for AWS to get faster when most organizations that I've worked in, certainly, things tend to slow down as we get bigger? So this brings me back to the science again. Why is it that metabolic rates slow down as size increases for mammals? Because as I say, an elephant is about 10,000 times heavier than a mouse, say. But its metabolism is about 1,000 times slower than a mouse, which means that the elephant lives a lot longer than the mouse. The mouse, lives and dies in a very short period of time. The elephant lasts, 100 plus years, for example, and they don't get much cellular damage happening. They operate in a much slower rate, and this is down to the hierarchies of blood supply and the way blood evolution is optimized. Blood supply and kind of arterial networks in both the mouse and the elephant. And this is kind of an interesting thing, right? So the way the hierarchy, the circulatory system in mammals has developed is that you've got this big heart, you've then got a series of branching arteries until you reach the capillaries. Now, you have to have capillaries because the viscosity of blood, when it hits a capillary, slows the blood down to the point where nutrients can cross the boundary to the cells surrounding the capillary. But you also have to have some number of layers, at least one layer of arterial flow, because the heart is a pump, and so it has to actually pump something in a regular cadence. And so the point with mammals is mammals have evolved to be, the smallest has like one or I think two layers of artery from its heart and then hits capillary, and that's the Etruscan shrew. Would you believe it's the size of my thumbnail? Whereas the biggest at the moment, of course, on land is sort of the elephant, and in the sea is blue whales. But the only difference between the Etruscan shrew and a whale is the depth of the hierarchy in their networks. Another interesting thing that's happened that evolution is optimized for is what happens when arteries split, when they branch. So when arteries branch, the two branches are exactly the same cross-section when you add them up as the artery they branched from. And that's really important, because if you didn't have that, what you'd get is essentially blood rebounding, because fluid mechanics, off the split, and it would apply essentially back pressure back through the circulatory system on the heart. The heart would be essentially beating against itself. So over the years, evolution is optimized for these exact splittings of arteries from one into two, with the area conserved. And this is interesting from the perspective, of course, this is why we don't like plaque buildup, right? We don't want furring in our arteries, because it's doing the same thing. It's causing back pressure in our circulatory system, causing back pressure on our heart, causing our heart to work harder and leading, in awful cases to heart attacks. But there's something else going on here as well. As I said, the depth of the circulatory system is another thing that causes this metabolic rate slowdown. So the depth of the circulatory system in a whale versus the depth of the circulatory system in a mouse, and then having these self-similar capillaries at the bottom. So the depth of the network, it implies slowing down of metabolism. That is essentially, the math shows, the deeper the network, the slower things get. But you've got, as I say, these self-similar things at the bottom, the invariant terminating units, which are the cells. And of course, the hearts are much, much bigger. And that's also true for things like water supplies. So the water supply to a smaller city, the pipes that lead into it are actually, versus a bigger city, the pipes that lead in, the source of the water supply are actually smaller in the smaller city. So this is the thing about bigger animals are essentially more efficient. They operate in a slower way, and this is due to this hierarchical network and this idea of impedance matching in the circulatory system. And this is driven by feedback from evolution. And this is true for companies. The same forces are operating on hierarchies and hierarchical networks in the companies in which we work. The reason you don't get twice as much out when you double the size is because you've got deep hierarchies imposing this limit, this scaling law limit of sublinear scaling. And companies are optimized by market forces, as I say. But this is the thing with companies, as they get older, they also slow down. It's very different for mammals, because mammals are born, they grow to a certain size, and then they tend to live at their life at that size. Well, there is no limit to the size that a company can grow to. A company is born somehow in a startup, it then ages and gets potentially bigger and bigger and bigger and bigger and bigger and bigger. And as companies get bigger, like mammals, they slow down. And you can sort of think of this, by thinking about the flow of work intellectually, by thinking about considering how work flows in the organizations in which we work. So this is an example of a value stream map, which, if you think of a value stream map, it's like a slice through the corporate information flow, essentially, from where work is sort of specified to where work gets done. And as you can see in this you're not supposed to read the detail of this, but the point being, there are lots of queues everywhere in this value stream map. So essentially, work gets specified at some point, it's then handed over to another department where it sits in an inbox, if you like, for a while, and then work is done on that thing, it's handed over to another department where it sits in an inbox, gets to the top of the queue. This is a classic kind of software development life cycle, but it's also how supply chains work. It's also how most work gets done, just full stop. Work gets specified and then moves through a set of information, a set of stages until it's completed. And a lot of the time, it's sitting in queues. But the interesting thing is that queues cause a tremendous amount of damage in organizations. In fact, Don Reinertsen says in the Principles of Product Development Flow, the best way of managing or improving the flow of work in a company or in your process is to manage queue size, queue depth. Don't look at anything else, just look at how deep your queues are, queues of work, because queues lead to all sorts of sort of pathologies. Essentially what we're doing when we create JIRA queues, or when we create queues of work that's waiting to get done, we're putting deliberate blocks into the flow of information through an organization. Whereas if you think about the ideal principle from Lean of single piece flow, that's a single bit of information flowing unimpeded through any of these queues into a, quote, production system or whatever. But when we're adding these queues in, that's what we're doing. We're doing the equivalent of blocking the corporate arteries in the same way that when I eat too much French cheese, I'm at risk of clogging my real arteries. So that's a bit about the effect of queues in organizations. But what about corporate metabolism? What happens with corporate metabolism? Why do companies slow down as they get older? Well, it's because in general, companies, as they scale, they add more processes, they increase the length of that information flow because they are adding more hierarchy. Things need to go through more stages to get stuff done, and therefore the flow of work, the flow of value slows down. And this is behind the research points to the fact that this is behind this idea of 85% of the revenue, not 100% as you double in size. So this is about the hierarchies in which that our companies have. With hierarchy, it is inevitable. It is inevitable that things will slow down. As you add more hierarchy, things get slower, and things get slower, and things get slower. Therefore, things slow down. But we also do this thing where we deliberately block our corporate arteries by putting blockers in, deliberately putting blockers in. So this led me to ask, whether we could identify the signs of aging in the organizations in which we work. And I think we can. I think there's some research that's been done that I mentioned at the start, from the State of DevOps reports over the last few years with Dr. Nicole Forsgren as first author on those, the research that's summarized in the book Accelerate, I think that research points to leading indicators to identify the signs of aging. If you haven't come across this book yet, it's fantastic. Half of it is summarized results, and then a proportion of the book is the research methodology, which is fascinating in itself. But I think this is one of the most important pieces of work that's been done over certainly in my career, I would say, in software engineering. And in that, they identify 4 key metrics that I think are the equivalent of taking your blood pressure or checking your heart rate or taking your temperature, the things that your doctor, your MD would go to, would immediately check if you were presenting with something, with an illness. So, mean time to recovery, how quickly you can get better, the cycle time, how quickly you go from development, from pushing a commit into production, change failure rate, how often changes you push into production fail, and the number of deploys per unit time. I think by taking a look at these and actively measuring these, this gives us a pretty good sense of how healthy the organization that we're in is. As I say, the equivalent of getting, checking your blood pressure and heart rate and so on. Obviously, you need to look deeper than these, but these are a good leading indicator. So, can we identify the signs of aging? I think we can. I think we can track the 4 key metrics and use these as leading indicators of how our team is doing, how the organization that we're in is doing, but also, because Conway's law, that also applies to the software that we're building as well. How healthy is the software that we're building? It's like monitoring heart rate and blood pressure. But I should point out, if we're in hierarchies, if we're in a hierarchical organization, we're limited, like the improvements that we can make in these things are limited by the scaling law operating, by this 85% factor that is imposed by the hierarchy itself. I should get on to, this is probably the most depressing bit. Companies also die, unfortunately, or fortunately, depending on your political, on your politics. But companies die all the time. I was really surprised. The research seems to show that every 10.5 years, there's 50% churn on the exchanges. So, there's a half-life of 10.5 years for a listed company before they're either bought by someone else, they fall apart, they go bankrupt, etc. So there is this idea of corporate mortality. And why is that? Well, it seems to be, this research seems to show, and again, there's less data because, of course, privacy, but it seems to be that as organizations age, they tend to spend less money on the things that made them successful to start with. And that is things like less revenue on research and development, new product development. They tend to sit back, rest on their laurels, and start, just gathering in the cash. And as they grow, they add hierarchy, so you get more process, more constraints. The hierarchy deepens, and you get this slowdown as well. So these hierarchies grow and grow and grow until eventually organizations sort of come to a stop. So, as I say, companies, they tend to gain economies of scale for infrastructure. That's good. You double in size, you don't need double the amount of network cable, say. But they also achieve sublinear growth in revenue with the same percentage, 85%. And eventually, over time, the organization's metabolic rate slows and slows and slows and slows, and eventually the organization passes away. But it's not all bad, because there are other examples we can point to which display different types of scaling laws. This type, in fact, of scaling law that AWS is displaying. Because there's another type of scaling law, which is super exponential growth or returns to scale. So as one company doubles, the other quantity more than doubles, related back to what I was talking about at the start with AWS. And cities do both. Cities have both types of scaling law in operation. So the first one for cities is the sublinear growth for infrastructure. So this does, again, that's for petrol stations and that kind of stuff. But for socioeconomic factors, they display super exponential growth, super linear growth. So for innovation, for wage growth, number of professionals, crime, but also crime, disease, and pollution, they display this returns to scale as opposed to economies of scale, which they display for road length, petrol stations, etc. Oh, fun fact, also walking speed is included in this. It's a slightly different power law, but as you double the size of a place up to the limit of your legs, people will walk faster. That's actually a real physical thing. That was there was some research done by MIT using a huge tranche of mobile phone data, and the bigger the place, the faster people walk, which is quite fun. But cities do both. They've got this socioeconomic thing with superlinear and then infrastructure, which is why they're so attractive, essentially why they drive growth. And that's because cities and the socioeconomic networks in cities are a different type of fractal network. They're not hierarchical. They are this idea of a small world or like social networks, essentially. And cities tend to grow by adding little bits on the outside, these new social, small world fractal space filling networks. There's actually a fun fact where you can measure the health of a city, and this was done with Detroit over a number of years, by measuring the fractal dimension of the city's outline. So if you measure the fractal, how crinkly essentially the boundary of the city is an indicator of health. The crinklier, the healthier. And in fact, when Detroit was suffering, over the last decade, the fractal dimension decreased. It got less crinkly. But as it's rebounded, the fractal dimension's gone up again. It's more crinkly again. And that's what's driving this growth in cities, the super exponential returns to scale, is the ability to add little bits onto the side, expand outwards, and also for the people in it to do the same, for the people in it to choose their associates. I don't know if you've come across these numbers before. It's often thought that there's only one thing called the Dunbar number, which is this idea of about 150 individuals who are your close acquaintances that you can keep in your head. But actually, the research that was done by, I believe it's Robin Dunbar, he discovered a number of these numbers. So 5 is the first Dunbar's number. This is the your closest family, your nuclear family, the people you live with, if you like. This is also awkward for me because there's 6 in my nuclear family. So either I love my wife or one of my kids less, which is a bit awkward. But that's the smallest one. Then you've got 15, which is the sort of your slightly extended family. Then you've got 50, which is your close family and friends. 150, your closest associates, and that's 500. And this is humans have evolved this structure, mentally over the years. Our brain architecture almost has evolved this structure as we've gone from dwelling in caves up to cities. As an example, this is my family. We were in Greece 2 years ago. This was my wedding. This is, one of the reasons weddings are generally in certainly the Western cultures that I've been to. Western weddings are in generally about 150 or so people, and then conferences. 500 sort of people in conferences is a fairly standard sort of size for a conference. And this also, the idea of a conference points to why cities are so powerful from the perspective of growth, because what happens with cities is that you get to associate with who you want. Now, the difference is from a village of 150 people, your Dunbar's number of 150 is everyone in the village. You don't get to choose who those people are. So you associate with everyone. Whereas in a city where you get the choice, you get to choose to associate with other lawyers or other software engineers for the bigger Dunbar's numbers. And it's this that is driving these returns to scale for innovation, for patents, for wages in cities, super exponential returns to scale. And as I said, this is based in human evolution, going from a small group living in a cave through to mega cities that exist today, all driven by socioeconomic super linear returns to scale. So I've sort of mentioned, we've got this idea of returns versus economy, and these are explained by the differences in the network design themselves. Hierarchical networks imply economies of scale, so sublinear growth. And this is for the teams that we're in. This is the organizations that we're in, around infrastructure, for example. But the other type of network, small world fractal space filling networks, they imply superlinear growth. So when you've got loosely connected individuals with no hierarchies present per se, then you get this superlinear returns. And as I said, cities, they tend to grow by adding little bits on the side, new little networks that emerge and are plugged in, increasing the fractal dimension, increasing the effectiveness, the returns as they grow. And if you've been keeping up with sort of, better practice, I guess, in team design, team topologies, all these kinds of things, this is potentially sounding familiar. Also, things like the microservice architectures, where we're trying to organize around things like business capabilities that are loosely coupled by events. We're trying to build little bits onto the side that are very, very loosely coupled without hierarchies, without having one service call another service call another service, or orchestration across many, many different services. This is why the popularity of event-driven architectures, I think, have been driven up by this idea of trying to create independent, cohesive, decoupled components in our software. So, to summarize that a little bit, as cities grow, they gain economies of scale for infrastructure and returns to scale for socioeconomic factors. Plus, they don't die, which is a bonus, generally. Essentially, they're so successful because they get 115% more stuff for 85% of the cost. Whereas for organizations, typically, as they grow, they get 85% more stuff for 85% of the cost. It's not bad, but it's not Amazon, it's not AWS. So I think it's not just AWS. I think there are other existence proofs that out there in the market, the organizations that we interact with quite a lot. So, Spotify, I would argue that the Spotify model of, squads and then loosely coupled together into bigger structures with, loose groupings across different roles and things, the Spotify model, I appreciate it's not exactly what Spotify do now, but as it was originally described, I think that's an attempt to create small world networks of these teams in an organization with as little hierarchy as possible and as much governance pushed down to the small world networks at the bottom. Thoughtworks, we could argue, and my colleague will probably be laughing at this, but I think Thoughtworks is actually an example of this. I haven't run the numbers for us, I probably should do, but as we've grown, rather than favor growing bigger and bigger offices, we've tended to open in more regions. So, there's a reason we've got 5 offices in China. I think it's 5, it might be more now, rather than one big office in Beijing. We've got 5 dotted about the place. And, our offices tend to max out at about 150 to 200 people. Certainly that's true in the UK. We've maxed out, we've got 2 offices around 200 or so, 150 or so people each. Valve, the computer games publisher and games developer, they famously published, leaked their employee handbook, and it had small world networks in it as how they wanted to organize themselves. Another example of an existence proof out there. And then finally, back to the one I talked about at the start, AWS, Amazon. And I think it was incredibly smart, because back in the day, I believe Jeff Bezos is actually a patron of the Santa Fe Institute. I believe he actually lives pretty much next to it, or quite close anyway, in that area. And there was this forcing function essentially of creating 2 pizza-sized teams, only talking via externalizable interfaces. These sort of things that led to the creation eventually of AWS itself and the restructuring of Amazon into the business it is today. I think these forcing functions created small world networks within Amazon and certainly within AWS. These constraints, deliberately imposed constraints, meant that the teams were organized in a particular way around social networks. And as I said back at the start, interestingly, their revenue figures point to the fact that they are growing super exponentially. They're experiencing super linear returns to scale. So, as most companies get bigger, it gets harder to get bigger. But as Amazon gets bigger, it gets easier to get bigger. They're adding these more teams on either side next to one another based on sitting on top of a common platform. They're able to create new products incredibly quickly because the teams are decoupled from one another. And I think these other organizations are attempting to do the same, either by accident or by design. I'm not sure. But that seems to be, the higher the fractal dimension, if you like, of your software development capability, the higher the fractal dimension of, therefore, your software architecture, the healthier, the more sort of, the healthier the organization and also the software architecture. So I'm going to kind of summarize. I hopefully have maybe a minute for questions. But I said at the start, quantities that do not change when other parameters of the system change, they play a special role in science. When we see these straight lines, it's interesting to go out and identify why. Can we come to some underlying principles? And back to what Martin and I said, we can attempt to describe what we see as these common characteristics. And it's interesting because, if you squint, a lot of those common characteristics are really about creating small world networks. They're about decoupling, they're about cohesion in architectures and in teams. It's about creating, loose coupling between cohesive components. All these different things talk to that. Breaking things up by things that don't change very often, the business capabilities, componentization into smaller bits that can interact. I'll leave you with this. So social network effects imply super exponential growth, and sublinear growth hierarchies imply mortality. So I guess what can we do as a takeaway from this? Can we think about this in terms of our own teams, of our own software architectures? Now that we have some of this research that points to this organizational style as being linked with higher returns or higher economic value from the perspective of the companies we work in, the products that we're building, and what does that mean for how we structure ourselves going forwards? And question hierarchies. Oh, and I should probably put every now and again, take your blood pressure and your heart rate, mean time to recovery, 4 key metrics, and so on. So this is the research summarized in these books at the top, more or less, but also I've put a selection of the original papers, the original research in there as well. So there's stuff about cities, there's stuff around the biological scaling laws and how it employs the revenue per employee, and a bunch of stuff around how scaling laws apply to biology and mammals. So that's pretty much me. I've come in just under time, so I've got maybe time for a question if someone wants to ask one.